In this video, we're going to talk about groups of orders 1 through 3. Now, I could tell you everything that there is to know about groups of orders 1 through 3 in just a few sentences, maybe even just one sentence. But we're going to take our time here and develop some tools and some framework that will help us when we get further down the line. As a warm-up here, let's talk about groups of order 1. The main thing to observe here is that if we have a set G with just one element in it, then there's only one possible way of defining a binary operation on G. Remember, a binary operation on G is just a function from the Cartesian product of G with itself to the set G. And since the domain and the codomain here both have cardinality 1, there's only one possible way of defining such a binary operation, which is by the rule that G star G is equal to G. Now, we claim that this binary operation turns G into a group. So there are three things that we need to check. First of all, we need to check that the binary operation is associative. Well, if I compute G star G star G, first by putting the parentheses on the left, then it's easy to see that I get the same thing as if I compute it by putting the parentheses on the right. Since there's only one element in the set G, this shows that the binary operation is associative. How about the existence of the identity? Well, there's only one possible choice for the identity element, and since when I star that element with any other element of the group, I just get back that element, it does indeed play the role of an identity element. And how about inverses? Well, again, there's not a lot to check here. Since G is the only element of the group and G star G is equal to the identity, it means that G inverse is equal to G. So G is its own inverse and we're done. Now, we didn't really have any flexibility in any of these decisions, so that means that there's really only one group of order 1. But if you think about it, we could have called the element of that group something else, and we could have labeled the binary operation differently. That would have made things look a little different, but it wouldn't have changed the essential algebraic structure of the underlying group. Therefore, to be precise, we say that there's only one group of order 1 up to isomorphism. We're going to talk a lot in later videos about what isomorphism is. But because I don't want to be too hand-wavy about it, let me just go ahead and give you a preview now. What I was saying before is that there are other conceivable ways that we could have labeled the set G, and there are other conceivable names that we could have given to the binary operation. But after relabeling, these are all essentially the same as algebraic objects, and that's what we mean when we say that they're isomorphic. In order to generalize this notion and to make it more precise, let's suppose that I have two groups, G with a binary operation of star and H with a binary operation of circle. We say that these two groups are isomorphic if there's a bijective map phi from G to H satisfying the property that phi of G1 star G2 is phi of G1 circle phi of G2 for all elements G1 and G2 in the domain. In other words, the two groups are isomorphic if there's a bijection between them which preserves the algebraic structure, so that if I combine two elements in the domain using the binary operation in the domain and then map the result to the codomain, I'll get the same thing as if I map each of the individual elements to the codomain and then combine them using the binary operation in the codomain. The map phi in this definition is what's called an isomorphism. And while you don't really need to worry too much about this right now, I want to give you the actual definition instead of just dancing around it. Also, the notation that you see here is a common notation for denoting that two groups are isomorphic to one another. Next, I want to talk about something that will be useful for us for getting started here, and that is the multiplication table for a binary operation. If I have a finite set S1 to Sn, and I have a binary operation star on the set S, the multiplication table for that binary operation is the n by n table whose ijth entry is Si star Sj. The entries in the multiplication table here are the ones in orange. And it's important to pay attention to the order, because since I don't know that the multiplication table is commutative, Si star Sj may not be the same thing as Sj star Si. Now, multiplication tables are really only useful for dealing with groups of very small orders, but one thing that I will say is that they do give you one way of telling when two groups with the same order are isomorphic. If you just look at the definition of isomorphism, then you should be able to see that it implies that two groups G1 and G2 are isomorphic if and only if there's a bijection between them which preserves the corresponding elements of the multiplication table. I'll show you some examples later on, in case it's not clear what I mean. Let's talk now about groups of order 2. Suppose that G is a group with order 2, written multiplicatively, and consider the possibilities for the multiplication table of this group. Now, the multiplication table of a group has to satisfy extra requirements that the multiplication table of an arbitrary binary operation doesn't necessarily satisfy. So that puts a lot of restrictions on what we can put in these empty boxes. If G is supposed to be a group, then one of the elements needs to be the identity element, and I've labeled it as E here. The fact that E is the identity element means that number 1, E squared has to be E, so that tells us that the entry in the top left corner of the multiplication table is an E. And similarly, the facts that EX and XC are both equal to X forces the top right and bottom left entries of the multiplication table to be X. Now if G is a group, then the element X has to have an inverse element. And since the identity element is not its inverse element, that forces X squared to be the identity element. That means that if G is a group with order 2, whose elements are labeled as E and X, then its multiplication table has to look like this. This multiplication table defines a binary operation on the set G, and it's easy to check that it's associative, that E plays the role of an identity element, and that every element has an inverse. Therefore, the set G, together with the binary operation defined by this multiplication table, defines a group. Furthermore, since we didn't have any flexibility in choosing how to fill in the elements of this multiplication table, we can also conclude that there's only one group of order 2 up to isomorphism. Well, now that I've said that, let me test you by showing you another group of order 2. If you take the collection of numbers -1 and 1, together with the binary operation of multiplication, which is a well-defined associative operation on this set, then the number 1 plays the role of an identity element, and the element -1 is its own inverse. So this does indeed define a group of order 2. So the question is, how can there be another group of order 2 besides the one that I just showed you? Well, of course, the answer is that this group is isomorphic to the group above. And you can see that pretty clearly if you just arrange the elements of this group in the multiplication table as I've done here. If you relabel the 1s as E's and the -1s as X's, you end up with exactly the same multiplication table as the one for the group that we saw before. That means that these two groups are isomorphic to one another. Now, let's use the same strategy to see if we can classify groups of order 3 up to isomorphism. Let's suppose that I have a group G of order 3, and let's label the elements as E for the identity, and then X and Y. Well, first of all, because E is the identity, when I look at the first row or the first column of the multiplication table here, I'm going to see E, X, Y, X, and Y. So that already gives me 5 entries in the multiplication table. Next, let's try to see what we can say about what XY could possibly be. If XY were equal to Y, then because of the cancellation law that we talked about in the previous video, it would force X to be the identity. But then there would be 2 identities, which we know can't happen because of the uniqueness of the identity that we proved in the previous video. So XY can't be Y. Now, if XY were equal to X, then also by the cancellation law, that would force Y to be the identity. Again, because of the uniqueness of the identity, that can't happen either. There's only one choice left for XY, and it has to be the identity. Now, by a similar argument, we can also show that YX has to be the identity. So that takes care of those 2 entries of the multiplication table. Next, let's think about what the possibilities are for X squared. First of all, if X squared were equal to the identity, then that would mean that X inverse is equal to X. But we already know from our previous step that X inverse is equal to Y. So that would contradict the uniqueness of inverses. And that means that X squared is not equal to the identity. If X squared were equal to X, then by the cancellation law we would have that X equals E, which would contradict the uniqueness of the identity. Therefore, X squared is not equal to X. So the only choice left is X squared equals Y. Now, by a similar argument, we can also show that Y squared has to equal X. So that fixes the multiplication table. And since we didn't have any choices except for how to label the elements, our conclusion is that there's only one group of order 3 up to isomorphism. Now, don't worry, because when we get to groups of higher order, they are going to get a lot more interesting. But before we move on, I'd like to first of all make 3 comments. The first comment is something which you may or may not have noticed. All of the multiplication tables that we saw for groups of orders 1, 2, and 3 were symmetric about the main diagonal. And whenever that happens, it means that you're dealing with an Abelian group. If you think about it, for the multiplication table to be symmetric about the main diagonal means that for all elements gi and gj, gij is the same as gjgi. So it means that the binary operation is commutative. The second comment, which is one that I'd like to spend some time on, is that all of the groups that we've seen so far in this video are examples of cyclic groups. Cyclic groups are important building blocks in group theory, and we're going to have a whole video on cyclic groups later on. But I'd like to go ahead and give you the definition and some examples right now. A group G is called a cyclic group if there exists an element little g in G with the property that every element little h in G can be written as g to the n for some integer n. In this case, we call the element little g a generator or a generating element for the group G. A convenient notation that goes along with this is the following. For any element x in a group G, if we write triangular brackets x, we mean the collection of all group elements of the form x to the n, where n is an integer. This is, of course, assuming that G is written multiplicatively. If G is written additively, then when we write triangular brackets x, we really mean the collection of all group elements of the form nx, where n is an integer. But of course, these are two different notations for the same thing. The top is the multiplicative notation, and the bottom is the additive notation. Now, with this notation, the definition of a cyclic group becomes the following. A group G is cyclic if and only if there exists an element little g in G such that the group G is equal to triangular bracket G, in which case we say that the group is generated by the element little g. Now let's look back at the examples that we've constructed so far to verify that they satisfy the definition for being cyclic groups. First of all, in the group with one element, if I raise that one element to any integer power, then I just get that element back. Remember from the previous video that g to the 0 is defined to be the identity element, which is g in this case. G to a natural number is just g times g times g n times, and g to the negative of a natural number is just g inverse times g inverse times g inverse n times. In all of those cases, since we're dealing with the binary operation that sends g times g to g to the n is equal to g, which means that this group is generated by the element little g. So it's a cyclic group with one element. Our notation for the cyclic group with one element is C1, so G is isomorphic to C1. Now let's consider the group with two elements. Which of these two elements do you think is a generator for the group? Well, it's certainly not the identity element, because no matter what power you take the identity element to, you just get the identity element back, and you'll never get x. On the other hand, if you consider the powers of x to the 1 is just x, and from the multiplication table you can see that x squared is equal to the identity element. Since the powers of x trace out the entire group, it means that the group is generated by the element x, so that G is isomorphic to C2, the cyclic group of order 2. Now you may be wondering what happened to the other powers of x, and that's a very good question. We know that x to the 0 is the identity, that's just by the definition of x to the 0, and x to the 1 is x, and we already saw that x squared is equal to the identity. Well, if I multiply x squared by x to get x cubed, that's the same as multiplying the identity times x. So x cubed is really the same as x to the 1, which is x. Now if I multiply that by x again, I'm just going to get x squared back, which is the identity. So x to the 4th is also equal to the identity. Now if I multiply by x again, I'm going to get x, and the pattern continues like that, alternating between the identity and x. I can also think about what happened to the negative powers of x. And first of all, if you observe that x squared is the identity, that means that x inverse is equal to x. Now if x inverse is equal to x, then x to the minus 2 is the same as x squared, which is the identity element. And if x to the minus 2 is the identity element, then when I multiply that by x inverse, I find that x to the minus 3 is x again. And the pattern continues. The fact that the powers of x cycle around like this between the different elements of the group is one reason why these are called cyclic groups. Now let's look at the group with 3 elements. Since I already told you that this is a cyclic group, which of these 3 elements do you think we could choose as a generator for the group? Well, it's certainly not going to be the identity element, so you have to choose between x and y. Now, actually in this case, both of these elements are generators for the group. And that's worth pointing out, because I never said that the generator for a cyclic group has to be unique. For this example though, let's just pick x and see what happens when we start to take powers of it. First of all, x to the 1 is just x, and from the multiplication table, we can see that x squared is y. Now to figure out what x cubed is, we just think about what happens when we multiply x by x squared. Well, that's the same thing as x times y, which is the identity element. Therefore, the element x generates this group. and it's isomorphic to C3, the cyclic group of order 3. Now, just as in the previous example, if you keep taking higher powers of x, they're just going to cycle around, and it's pretty easy to see why that happens. That's something that we're going to take a look at in more detail in our video about cyclic groups. But if you think about the division algorithm, or if you know something about the integers modulo 3, then maybe you can already see what's going on here. Now, I know you thought this was just going to be a video about the groups of orders 1 through 3, but while we're here, I'd like to take the opportunity to tell you just a little bit more. It's an important fact that for each natural number n, there's exactly one cyclic group of order n up to isomorphism. So in practice, even though you may encounter cyclic groups of the same order that are presented differently, any two finite cyclic groups of the same order must be isomorphic to one another. Cyclic groups can come to us in multiplicative or additive notation, and here I'm writing things in multiplicative notation. So if I'm talking about a cyclic group of order n generated by an element x, then it must consist of the elements x to the 0, which is the identity, x to the 1, x squared, and so on up to x to the n minus 1. If you start from the identity and you multiply by x again and again, you go to higher and higher powers of x until you get to x to the n minus 1, and then when you multiply by x again, you get back to the identity. Similarly, if you start from the identity and you multiply by x inverse, you cycle through the elements in the opposite direction. Now, I'm not going to go through all the rigorous details to prove what I just now said. We can leave that for a later video. But I just want to put this in your head for now so that you can think about it. There are different notations for the cyclic group of order n, and most of the time I'm going to use the notation as Cn, but other common notations are Zn or blackboard Zn. Cyclic groups come up in a variety of different contexts, so I'd like to try to mention a few of them here. First of all, when we talk about the integers modulo n under addition, this is going to turn out to be isomorphic to the cyclic group of order n, just written additively instead of multiplicatively. Next, there are many problems where one is led naturally to consider the collection of nth roots of unity in the complex plane together with the binary operation of multiplication. It's pretty easy to see that this group is also isomorphic to the cyclic group of order n. And finally, another natural place where you see cyclic groups arise is when you're considering the collection of rotations in the plane, which preserve a regular n-gon centered at the origin. Here, n is bigger than or equal to 3, and noting that the set here is a collection of maps from R2 to R2, the binary operation is composition of maps. Anyway, before we get lost in all of this, my point here is that the group of rotations in the plane preserving a regular n-gon centered at the origin is also isomorphic to a cyclic group of order n. Now, because this is closely related to another group that we're going to see in the next video, I'd like to take a closer look at it so that you can understand more carefully what it's talking about. To give a concrete example of one of these rotation groups, let's let n be 3, and let's consider the collection of all rotations in the plane which preserve an equilateral triangle centered at the origin. If we write r theta for the counterclockwise rotation about the origin by an angle of theta radians, then it's pretty easy to see that the only rotations which will preserve an equilateral triangle centered at the origin are rotations by 0 radians, 2 pi over 3 radians, or 4 pi over 3 radians. Now, first of all, I'm claiming that this collection of rotations, together with the binary operation of composition of maps, is a group. So I need to check 3 things. Well, actually, first of all, I need to think about whether or not the binary operation is even well defined on the set G. It is worth stopping to make sure that that's true, and that's something which you can check. If you compose any 2 of these maps, you always get another map in this set. So the binary operation is well defined. And now I can move on to check that this is actually a group. Associativity follows from the fact that composition of functions from a set to itself is always an associative binary operation. That's something which I'm going to leave it to you to check, but it's not too difficult. It's also pretty easy to see in this case that the map R0 plays the role of an identity element. That's because if I compose the rotation by 0 radians with the rotation by theta radians, either from the left or from the right, I just get a rotation by theta radians. It doesn't even matter what theta is here, so it's certainly true for all the elements of this group, which means that I have an identity element. And how about inverses? Well, of course the identity element is its own inverse. That's always true. So I'm left with the problem of deciding whether or not R2 pi over 3 and R4 pi over 3 have inverses in the group. Well, if I compose r2 pi over 3 with r4 pi over 3, then, working from the right to the left, I'm rotating by 4 pi over 3 radians and then by 2 pi over 3 radians. And the net effect is that I'm rotating counterclockwise by 2 pi radians. Well, even though it seems like I did something there, since the composition of these two functions maps every point of R2 to the same point, it's the same as the identity map R0. The same thing is true if I compose them in the other direction. If I perform the operation R2 pi over 3, and then I perform the operation R4 pi over 3, the net effect is to rotate by 2 pi radians, which again is just the identity map. That means that the inverse of R2 pi over 3 is R4 pi over 3, and the inverse of R4 pi over 3 is R2 pi over 3. Now that I know that every element of this group has an inverse, I know that this is a group. Finally, since this is a group with 3 elements, and we know that there's only one up to isomorphism, and that it's isomorphic to the cyclic group of order 3, let's try to identify a generator for this group. If you were paying attention when we looked at groups of order 3, you should know that both R2 pi over 3 and R4 pi over 3 are generators for the group. Let's just pick one. Let's write R for the transformation R2 pi over 3. Then R to the 0 power, by definition, is the identity element, which is R0. And R squared, which is R composed with itself, is R4 pi over 3. So the group G is generated by the element R. And, as we already knew, G is isomorphic to the cyclic group of order 3. Now, while we're here, I feel that I need to tell you one more thing. Besides the finite cyclic groups that I just told you about, it turns out that there's one more cyclic group, but it's an infinite one. Can you guess what it is? Well, if you thought of any infinite cyclic group, then technically you got it right, because every infinite cyclic group is isomorphic to the collection of integers under addition. The collection of integers under addition is generated by the element 1, because it's the collection of all things of the form 1 plus 1 plus 1 n times, together with their negatives. Don't be confused here because I'm using the additive notation for the group generated by 1. And this is a good example of what I told you about how we often switch back and forth between additive and multiplicative notations when it's appropriate. Anyway, that's enough about cyclic groups for now, so we'll just let that go until a later video. Now, a while ago I told you that I had 3 comments, but my second comment was really a long digression about cyclic groups. So now I have to return and tell you the third one. The third comment, which may seem a little depressing at this point, is that looking at multiplication tables is really not a very good way to try to understand all the groups of a given order. You might already believe me about that because of the amount of effort that we had to exert just to classify all groups of order 3. But when n gets bigger, it's really a lot harder. So for example, if we just consider the collection of binary operations on a set of cardinality n, there's already n to the power n squared operations. Now, that's a huge number. When n is just 10, it's already a googol. And even though you can rule out most of those binary operations because of the other group axioms that have to be satisfied, looking at multiplication tables still just isn't a computationally feasible way to try to classify groups of order n. In later videos, we're going to develop better techniques though, so that's something to look forward to. Well, that's the end of this video. In the next video, we're going to continue by listing all groups of orders 4 through 8 up to isomorphism. This is where you start to see some interesting groups, so make sure to tune in for this one.